Welcome back to this hypersonic small disturbance equation, right? So, in the last class, okay, we acknowledge hypersonic and high temperature gas dynamics by John D. Anderson, right? So, in the last class, we had a discussion basically on the governing equations, right? And then we had a discussion on the approximate methods and why we are going for uh, the flow field now, right? Previously, we had a discussion on the body shape and the surface pressure on the body, but the first time we are looking into the flow physics, right? So we have made a discussion on slenderness ratio, and we have derived all these things, and finally we understand that m infinity tau is um, like it is a kind of hypersonic similarity parameter, which is almost similar to that k value k is equal to m1 theta. Now, we know the governing equations, basic governing equations, right? So here, let us let us now express the steady Euler equation in terms of perturbation velocities u dash and v dash. So I say steady Euler equation, and hence see since it is a steady Euler equation, we will be neglecting the terms with respect to time, right? So probably these terms will be neglected, right? So let us start the Euler equation. So the assumption here is the steady Euler equation. Okay. So steady Euler equation, and we try to write the steady Euler equation in terms of the perturbation velocity u dash and v dash. Okay. So here now the equation will become, say, for example, the u component. Say, let us say the u component. U component, you know already, it is v infinity plus u dash. Similarly, the v component, that will become u dash becomes 0, so only you have v dash. Similarly, the w component, the w component becomes w dash. Right. So now applying that in a steady set of equations, then we can write, say, we can write the whole governing equation. So let us say the first equation we can write dou by dou x of rho v infinity plus u dash, because I want to represent that in terms of u, right? So dou u by dou x I write in terms of dou by dou x of v infinity plus u dash, plus dou by dou y of rho u dash plus dou by dou x of rho w dash, that is equal to 0. Okay. Now let us write the x momentum equation. Okay. So rho into v infinity plus u dash into dou by dou x of, we need to remember one thing, we are considering only the steady set of equation, hence we don't consider the time term, right? Dou t plus rho v dash into dou by dou y of v infinity plus u dash plus rho w dash into dou by dou z of v infinity plus u dash. That can be equated to minus dou p by dou x. Right? So I recommend you can also write the y momentum equation, right? Z momentum equation, right? So y momentum Z momentum equation in terms of the perturbation velocity, right? Now, okay, I recommend you to note that, right? X momentum, y momentum, Z momentum equation, and again we can also write the energy equation, right? So that is like E infinity plus u dash into dou by dou x of P by rho of gamma, right? Plus P dash into dou by dou y of P by rho of gamma plus W dash into dou by dou z of P by rho of gamma. That is equated to 0. Right? So it should be noted that the velocities are expressed in terms of perturbation, right? So perturbation relative to the free stream velocities, right? But have you noted here the pressure is not equated to P infinity plus P dash. Similarly, the density is not equated to rho infinity plus rho dash, right? So here we consider the P still as the whole term, similarly the rho, right? Okay. So this is a set of equation we have as of now. So this equation is in terms of perturbation velocity. Now let us non-dimensionalize the quantities. Say for example, we have a non-dimensionalization, right? So let us non-dimensionalize non-dimensionalizing, right? So non-dimensionalizing the quantities. Say quantities like pressure, density, and so on. So let us start with the pressure. So here, consider the oblique shock relation. We already know the oblique shock relation, right? Consider the basic oblique shock relation. See, ultimately we want to derive hypersonic small disturbance equation. Hence, we are deriving one by one and we want to finalize, right? So, let us consider the oblique shock relation for this dimensionalizing, right? Oblique shock relation, and we already know the consideration m infinity tends to infinity. So, again, also we should note that it is a slender body, right? In hypersonic flow, we usually consider the slender body, and if you say we consider a slender body, then um, the shock wave the shock wave angle, right? So you consider this. So if you have a theta and if you have a beta, right? So we have a consideration that theta and beta is, you know, small. So if theta and beta is equal to small, then we know sine beta can be equated to sine theta. That can be approximated as theta, and theta can be estimated by dy by dx. And you know already dy by dx, this is a dy and this is dx, right? So we already know that this term can be equated to tau, that is equal to d by l, right? So here we already had a term l, and here it is, right? So this is approximation for a oblique short relation, and the m infinity tends to infinity. We consider the theta is small and hence beta is small, and we can equate this to tau is, I mean, sine beta to sine theta, which is equal to theta, and then it is equated to dy by dx, and it is equated to tau. Now, we already know the basic equation, right? So, say pressure equation P2 by P infinity, that is equal to 2 gamma by gamma plus 1 m infinity square sine square b. So we already know a method called order of magnitude method, right? So I can write the pressure ratio P2, say P2 by P infinity. So I can write this as it is of the order of m infinity square and tau square, right? So this equation we can write in terms of the slenderness ratio, right? So this implies that the pressure throughout the shock layer, right, throughout the shock layer over the body will be of the order of P, that is P2, which is of the order of m infinity square, tau square, and P infinity. Right? So if it is so, then if I want to non-dimensionalize, then non-dimensionalize, right, non-dimensionalized pressure, and if I want to make it to the order of magnitude unity, then say in order to make the order of magnitude unity, order of magnitude to unity, so we can say that it can, any pressure which is divided by gamma m infinity square, tau square, and P infinity can be the better way, right? Better way of expressing it in a non-dimensional form, right? So if you want to non-dimensionalize a pressure, we can use this kind of notation, right? Okay, now let us go back to density, right? So you know that the density rho 2 by rho infinity. So rho 2 by rho infinity is equated to gamma plus 1 by gamma minus 1. And we know if we consider gamma is equal to 1.4, then rho 2 by rho infinity will become 6, right? Right? So in the case where we want to have a non-dimensionalized form of the density, we can have rho by rho infinity, right? So this is very simple. We can take it directly. Then let us go back to the third one, the velocity. Say we have a velocity u component, v component, and so on. So let us consider u2 by v infinity. So what is u2 by v infinity? 1 minus 2 sin square beta by gamma plus 1. Right. So again, to define the change in x component, right? The change in x component velocity. So the change in x component velocity across the oblique shot, we can express the del u that is equal to v infinity minus u, right? So I recommend you to proceed further. V infinity minus u2. So let us now calculate del u by v infinity. Say del u by v infinity. So we can write v infinity minus u2 by v infinity. So finally we can write this as 2 sine square beta by gamma plus 1. Right? You can simplify that. So this we can write that it is in terms of the order of tau square, right? Del u by v infinity, right? So this implies that the non-dimensionalized form of the perturbation velocity u dash, the bar I represent in order to say the non-dimensionalized form, right? And u dash is the representation of the change in velocity in x direction. And this can be defined as you see it is like u dash by v infinity and tau square, right? So in order to make the order of magnitude unity, so we can consider, so u dash is okay. Now let us calculate for v dash. We know v2 by v infinity, right? v2 by v infinity. So v2 by v infinity is sine 2 beta by gamma plus 1. So let us calculate del V by V infinity. That is equal to, again, V2 by V infinity. So finally, this can be written in terms of the order of tau, right? So for non-dimensionalized perturbation velocity, that is V dash, right? So we can write this as V dash by V infinity tau, right? Now, uh, okay, now let us have an discussion. Right? We have seen so far what we have done is initially we have written our equation, and we have made a point that it is a steady Euler equation, right? So we want to write in terms of perturbation velocities. So we have done it with u dash, v dash, w dash, right? So we and then we want to non-dimensionalize the quantities. Right? So we have finally non-dimensionalized the pressure, non-dimensionalized the density, non-dimensionalized the u dash, v dash, and so on. Right? Now, um, we already know that for hypersonic flow, so hypersonic flow, for hypersonic flow over a slender body, over a slender body, our tau, what is tau? Tau is a slenderness ratio. Tau is so small, correct? It is so small, and see this tau, this is tau, right? So tau is so small that this is a d and this is l, and tau will be always less than units. So tau is so small, and it is always less than unit. So you have okay. You see here del u, which is proportional to tau square, but del v, which is proportional to tau. Right? So we can write here that del u, which is proportional to tau square, and del v, which is proportional to tau. And I said tau is smaller and it is less than unit, right? So do you remember sometimes back we had a discussion that in a hypersonic flow over a slender body, the change in velocity in v dominates than u, right? Right? So major change in properties in the hypersonic layer, hypersonic shock layer over a slender bodies, which takes place across the flow rather than along the flow. That is what the conclusion from this book, right? So we can write that, say, here major changes. the major changes in properties in a hypersonic shock layer. So in a hypersonic shock layer, and please remember it is over a slender body. Over a slender body takes place takes place across the flow rather than along the flow. So, I mean, while doing this particular derivation, we understand that this particular point, right? The hypersonic flow on a hypersonic shock layer over a slender body, the change in properties takes place across the flow rather than along the flow, right? So please remember the major changes, right? Okay, I stop at this point for the this lecture, and what we will do is like we will have all non-dimensionalized form, and then we will apply it in the basic equation, and we will continue our discussion, right? So I stop at this point. Um, Thank you very much.